Welcome back to the AI Research Roundup. I am your host, Alex. Today we're looking at a paper that's been trending on Papers with Code called PerceptionLM, Open Access Data and Models for Detailed Visual Understanding. The core issue it tackles is that many of the best vision language models are closed source. Their data and training methods are kept secret. This makes it hard to measure real scientific progress. To get around this, researchers often use a technique called distillation, where a secret teacher model helps train their open models. But this paper argues that this obscures real progress. So they introduced the perception language model, a completely open and reproducible framework to build these models transparently, and they're releasing new data and benchmarks to help. And to back up that commitment to openness, the authors released all the code for this work. In their repository, you can find their state-of-the-art perception encoder and the perception language model. The perception encoder is the part of the system that, it sees an image or video and translates it into a numerical format. Then, the perception language model uses that information to generate descriptive text. The repository has everything you'd need, including model checkpoints, which are saved versions of the model, plus guides to get started with training and evaluation. Alright, and this first figure gives us a great overview of what makes this project tick. On the left, you see an example from their new fine-grained question-answering dataset. This dataset is not just about asking what is happening, but how, like the very specific direction of a paper fold. Next to it is the spatio-temporal captions dataset. This one links descriptions to specific objects and moments in a video, like tracking the dog's actions over time. And on the right, we see the perception language model itself, which combines that perception encoder with a Llama 3 model. So we've seen the components of the perception language model, but how do they actually train it? Well, this table lays out their 3-stage training recipe. First, there's a warm-up stage. Here, they only train the projector, which is a small component that acts as a bridge, connecting the vision part of the model to the language part. Then, in stage 2, or mid-training, they train the full model on a massive 64 million synthetic data samples. Finally, stage 3 is for supervised fine-tuning, or SFT. This is like a final polishing step, where they use high-quality, human-labeled data to teach the model those really difficult, nuanced tasks we talked about. And this table here really breaks down that data mix. You can see the bulk of the training, nearly 65 million samples, comes from their own synthetic data. This includes captions for images, documents, and different video types like exocentric, which is a third-person view, and egocentric, which is a first-person view. This synthetic data is all used in the early and middle training stages. But for that final, crucial, stage 3 fine-tuning, they use their new, high-quality, human-annotated datasets to teach the model those really difficult fine-grained tasks. So after seeing that they use a ton of synthetic data, the natural question is, does it actually work? And that's exactly what these plots show. These are called scaling plots, and they illustrate a really important concept known as a scaling law. This is basically a predictable relationship showing that as you invest more training compute, which is measured in GFLOPS on the horizontal axis, the model's average error on the vertical axis goes down. For general tasks like video, OCR, and natural image question answering, the trend is very clear. More compute leads to lower error, following a nice, predictable power law. But remember how those nice scaling laws were for the general tasks? The researchers found that for really hard questions, like understanding the tiny details of an activity, synthetic data just doesn't cut it. And this is where their new human-annotated dataset called Perception Language Model Fine-Grained Question Answering comes in. You can see on the left just how detailed the questions are, asking about the exact direction of movement or how an object is held. The chart on the right drives this home. For these nuanced categories, their new dataset is massively larger than existing ones, sometimes by over 40 times. And this plot provides the visual proof for that limitation of synthetic data. The bottom line for general video question answering shows that nice scaling trend we saw earlier. As you add more compute, the error drops steeply. But now look at the top line, which is for hard question answering. It's almost flat. Even as they scale up the model size, from 1 billion to 8 billion parameters, and pour in more compute, the error barely improves. This clearly shows that for these really tough, nuanced video tasks, simply scaling up with synthetic data just isn't effective. So to tackle that problem with hard video questions, the researchers created a second, really innovative human-labeled dataset. This one is called Perception Language Model Spatio-Temporal Captions. And what this image shows are examples of this new data. You see, it's not just a single caption for the whole video. Instead, each description is tied to a specific slice of time and a specific person or object in space. For example, a caption like "the person moves from right to left" is linked to a precise time interval and a pixel-level outline of the person, which they call a masklet. So what this work on perception language model really shows us is the critical need for high-quality, human-annotated data to push past the limits of current models. For AI to move beyond just general descriptions and truly understand the fine-grained, moment-to-moment details of what's happening in a video, it needs data that reflects that complexity. This research provides a fantastic, open-access resource for the whole community to build on. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.